And I'm live. That is cool. And today is 12th of September 2025, Friday. And today we will just continue. Yesterday we did in dynamic programming. Yesterday we did the rod cutting problem. Today is the matrix chain multiplication, in which we have to find a sequence in which to multiply matrices of different sizes so that we do the minimum amount of scalar multiplications. And what does that mean? We will look in that section of the chapter. Yep. So I will stop my video over here. That is cool. And this is not it. This is red black trees deletion. I was reading about deletion in red black trees, and deletion is quite complicated in red black trees. Yeah, it is. Insertion is not that complicated. Insertion is fine. Insertion is fine. Like, yeah, insertion is fine. But deletion is complicated in red black trees. Anyways, dynamic programming. Yesterday we did rod cutting, and that was fine. We even in rod cutting, in the rod cutting example, we even did all of these exercises, which was pretty cool, right? Which was pretty cool. And today, let's go through this section. Matrix chain multiplication. And again, to state it again, the goal is not to complete this thing, but whatever we do, we can clearly state it afterwards what we did. The goal is to have a clear understanding of what we have read. Even if we read a single line, we need to understand what that line means. And with that mindset, let's drink a bit of water. And you can look at this. Okay. And you can look at this. Martyrs. This is a French movie. And it is very strange. It is a very strange movie. And back to dynamic programming. So matrix chain multiplication. What is this problem? What does it even mean? Our next example of dynamic programming. And yes, before beginning, we have seen in the example which has been provided in this whole first part of this chapter, we did the rod cutting example, and in this they did state a few things, that there is a subproblem graph, which is a directed acyclic graph right here using yeah, it was written that this thing, not this thing, but this thing is a subproblem graph. And this is one way to represent our subproblems. And they stated 4 steps to find solution to a problem using dynamic programming. And the 4 ways are these that they stated yesterday in the book. Not that they stated yesterday, they have been there forever, but we read them yesterday. So, dynamic programming procedure. And in this, they stated, first of all, define an optimal solution, right? If you are looking for an optimal solution, you need to define what an optimal solution looks like, and define how to get an optimal solution from optimal solution to sub problems, right? If you can define the overall optimal solution, what would the optimal solution for the overall problem looks like? And also, if you have the optimal solution for sub problems, how can you find the optimal solution to your own big problem given solution to those sub problems? And third was to just find the optimal solution, right? First, you define what an optimal solution looks like. Then you define how you could find that optimal solution given optimal solutions to subproblems. And then there is the fourth step, which we don't always have to do. Construct the optimal solution. And this fourth step we don't always have to do, because most of the time the problem only involves giving outputting the optimal solution. Like, what is the optimal solution? Not the optimal solution, what would be the optimal value that you are finding out, not the solution which is giving that optimal value. Like, for example, if you want to maximize the value, generally the question only involves what would that maximum value be, and not that which solution gives that maximal value. So I guess that makes sense. And yep, so these were the four things which were stated yesterday. Even, yep, characterize the structure of an optimal solution, what an optimal solution looks like, then recursively define the value of an optimal solution, which just means if you have optimal solution for some sub problem, how you can find the optimal solution for your higher level meta problem, and then compute the value of an optimal solution, typically in a bottom up fashion. Yep, find the optimal solution, construct step by step from bottom up or any top down manner, and then construct an optimal solution from computed information. Yep. Construct the optimal solution. And today we will go to the next second part where they have stated another problem, which is matrix chain multiplication. And in this, we have been given another example of a problem which can be solved using dynamic programming. And with this example, we will strengthen our understanding of dynamic programming, or how we can apply dynamic programming to something else, to any general problem. And it is going to be cool. Let's see. Our next example of dynamic programming is an algorithm that solves the problem of matrix chain multiplication. Given a sequence chain AI to an of n matrices to be multiplied, where the matrices aren't necessarily square. Okay, matrices aren't necessarily square. The goal is to compute this a into 2, a1 into a2 into a3 into a till an using the standard algorithm. What is the standard algorithm? If we click on this thing, we will get to the standard algorithm, and the standard algorithm is like the standard algorithm, which is like this. Given two matrices, what is the standard algorithm? I don't know. If you have matrices like this, some values, and then the next one, I guess the next one has to be like this. If this is of size 3 by 3, this 3 is number of rows and this 3 is the number of columns, 1 2 3. Then the next one should have the same number of rows as the number of columns in the earlier matrix, which is correct in this case, into 2, that is the number of columns. And if we have A B C D E F G H I J A L M N O, what do we do? We multiply, and yes, the product that we get would be of size 3 by 2, which is a matrix like this, and that is a beautiful matrix. Wait, now that is beautiful. Something like this. And what goes in this one is A into I B into L, and C into N, and add all of these, and they will come here. And then for the next one, this into this into this, into C into O, and add the products, and that will come here. Then we move on to the next row, multiply the next row with this first column, and the sum of the product goes in this column, in this cell. And same for this whole row will be multiplied with this whole column, and the sum of the products will go here. And same for this row multiplied by this column, sum of the product goes here, and then this whole row again multiplied by this column, and the sum of the product goes here. That is cool. That is the standard way for multiplication, and what we want to do is reduce the total number of scalar multiplications. In this example, how many things did we multiply? We had this and this. So we multiplied these three things. 3 here, this 3 here represents this 3. So let's say we have two matrices of size I. Let's say we have two matrices of size, one is of size I into j, and another is of size j into k. Then what is going to be the total number of scalar multiplications? First of all, we will multiply all of these j's with these, all of these things. And yep, in total there are j columns in this, and every number in this column is going to be multiplied 2 times in this thing. Why 2 times? Because there are 2 columns in this. So the scalar total number of scalar multiplications is going to be j, which is the number of columns, each column, the number of columns, each column is multiple, not each column, but what is this? This is the number of columns, and each column is going to be multiplied k number of times. So j into k, and also for each column, I mean each column, there are 3 columns and there are 3 rows in this, and which is I. So multiplied by I, in total we will have I into j into k amount of scalar multiplications. Why is that? Because for each of these things here, each of columns here, each column here will be multiplied by each column here, and in total there are 3 rows. So that whole process of multiplying columns will be done 3 times over. So in total j, I is the amount of rows that there are, so that is how many times this whole process will go, and in each individual process we are multiplying every element in a given row with every element in a given column in the second matrix, and that multiplication is done for however many columns there are in this second matrix, which is j. So the total number of scalar multiplications is I into j into k for two matrices whose size are I, j, and j, k, and that is cool. Hi, good afternoon. How are you? And today we will do matrix chain multiplication, which is cool. It also uses some kind of numbers called Caladan numbers. No, shit, not Caladan. Caladan is like the home planet for Muad'Dib. Catalan numbers. Those are Catalan numbers. Yep, Catalan numbers. Sure, let's go with this. For multiplying rectangular matrices, we will see in a moment, while minimizing the number of scalar multiplications. you can evaluate the expression 14.5, this thing, using the algorithm for multiplying pairs of rectangular matrices as a subroutine once you have parenthesized it to resolve all ambiguities in how the matrices are multiplied together. That makes sense? Since you have an expression of matrices A1 to A2 into A3 into till AN, you can parenthesize and then you will know your sequence of multiplying the matrices. So then in how matrices are multiplied together. Matrix multiplication is associative. So A1 into A2 into AN equals A2 into AN into A1. So that is cool. The product of matrix multiplication is associative, and so all parenthesizations yield the same product. So we get the same product. All we have to do is reduce the total number of scalar multiplications that we have to do to get to that product. The product of matrices is fully parenthesized if it is either a single matrix or the product of two fully parenthesized matrix products, which means every matrix there are like brackets like this, and if you arrange matrices like this, then it is called fully parenthesized, because to solve everything else you first have a single one level solution that you have to do, in this case which is A2 into A1, and here it is A1 into A2 and then A3 into A4, and then whatever the product is, multiply them together. So that is cool. So matrices like this are called fully parenthesized. Either it is a singular matrix or a product of two fully parenthesized matrix. Here a singular matrix is being multiplied by a product of two singular matrix which are fully parenthesized. So that is cool. For example, if the chain of matrices is this, then you can fully parenthesize the product of A1 into A2 into A3 into A4 into 5 distinct ways. Okay, this is also another way. And yeah, Catalan is also chess line, right? Should I think so? I don't know. I don't know specifically. I haven't read chess theory. I know about Sicilian defense and Caro-Kann defense. How can you parenthesize a chain of matrices can have a dramatic impact on the cost of evaluating the product. Makes sense. Let's see why. Consider first the cost of multiplying two rectangular matrices. The standard algorithm is given by the procedure this. This thing takes three matrices actually. First and second are going to be multiplied with each other. This matrix will store their product, and P, Q, and R are their dimensions. And here it is given that A is of dimensions P into Q, B is of dimensions Q into R, and then C must be of dimensions P, R. And it is of dimensions P, R, because only then it makes sense to store the product in C. So for every row, P is the number of rows in A. For every row in A, you are going through every column in A which corresponds to every row. You are going through every column in the second matrix B, and individually for that column you are going through every row and column in A and B. Q represents a column in A and it also represents a row in the B matrix. And internally you are filling up Cij, I, J with all the variations with which come as a result of this K thing here. K in A represents the columns and K in B represents the rows. That is cool. The running time of rectangular matrix multiplication is dominated by the number of scalar multiplications in line 4, which is PQR. And why is it PQR? Because we have a loop inside a loop which has another insider loop, and in total this multiplication is done P into R into Q times PQR. Therefore, we will consider the cost of multiplying matrices to be the number of scalar multiplications. The number of scalar multiplications dominates even if we consider initializing C equals 0. To perform just C equals A into B to illustrate the difference. Yes, let's just see. Okay, so when we multiply two matrices, the cost of that multiplication we are defining by the number of scalar multiplications like this that we have to perform, and that is going to be P into Q into R. And PQR, P is the number of rows in the matrix A, Q is the number of columns in matrix A and also the number of rows in matrix B, and R is the number of columns in matrix B. That is going to be cost for multiplying two matrices A and B. And to illustrate the different costs incurred by different parenthesization of a matrix product, consider the problem of a chain. Let's say we have three matrices A1, A2 and A3 of three matrices. Okay, suppose that the dimensions of the matrices are 10 into 100, 100 by 5, 5 by 50 respectively, multiplying according to the parenthesization this. Okay, we can multiply A1 and A2 first, and then whatever the product is we can multiply that by A3. So A1's dimensions are 10 into 100 and A2's dimensions are 100 into 5. Therefore, the total number of scalar multiplications is going to be 110 into 100, which is 1000 into 5, 5000, which is going to be 5000 scalar multiplications to compute that. And then the resulting matrix will have a dimension of 10 into 5. And now, if you multiply 10 into 5 into 50 for the last matrix multiplication product, you will get 50 into 10, 500, 500 into 5, 2500, 2500, and our 5000 initially scalar multiplications when we multiplied A1 and A2. Therefore, the total number of scalar multiplications is 7500 now at this point when we have solved this whole thing. So, yep, A1 and A2 plus another 2500, total is 7500. Multiplying according to the alternative parenthesization, if we multiply them like this, that is multiply A2 and A3 and then multiply A1. By multiplying A2 and A3 first, the total number of scalar multiplications is going to be, for the scalar multiplication for A2 into A3 is going to be 100 into 5, 500, 500 into 50. What is 500 into 50? That is 2500. And in 2500, yeah, 25,000, because it is 5000 into 50, 5000 into 5, because 100 into 50, that is 5000, 5000 into 5, 25,000, and it has already exceeded the number of multiplications we did before in our prior parenthesization. And after that, when we have multiplied A2 and A3, we will have to multiply that product with A1, which involves 10 into 100 into 50. Shit, that is 50,000. So 50,000 plus 25,000, that is 75,000. 75,000 total scalar multiplications. That is a lot. How hard were 1200 iterative problems for you in TLE? I'm currently struggling in most of them and can do it without tutorial. Even if I solve it, solution is not optimal and gets TLE. I mean, I was struggling at 800 level questions when I was doing 800 level questions, and I was struggling at 1200, and I'm still struggling at 1500. But right now I have taken a break from solving questions. Right now I am beginning to read more about dynamic programming, and I will begin solving those 1500 questions after I have read and gone through all of this dynamic programming chapter, and it is going to be cool. And because it is okay, why are you facing problems in solving 1200 problems? What do you think after? Okay, let's say you read the problem and you came up with a solution and it didn't work. And then you read the editorial. What was the thing that you didn't know before solving that problem, which you came to know after reading the editorial? What was that specific thing? If you can figure it out and you can get better at figuring it out, if you can do that, it will be cool. So see what was the thing that you had to read from the editorial specifically, which you were lacking before reading the editorial. And if you can see what you were lacking, what you were lagging, now you know what you were lagging and now lacking, and now do not forget it. Okay, so that is cool. That is fine. You came up with the approach, but it was not optimal. So when you think of an approach, you can, by looking at the input size, you can figure out how much time it is going to take. And if you can do that, you will be able to figure out its time complexity. And you can also see what the time limit are for the question specifically. And then you can compare if your solution is going to be optimal or not before even implementing. So you don't have to implement and then submit and then see, oh, I got a time limit exceeded error. So this problem is easier to fix, time limit exceeded error. And yeah, so if you see that you are going by after calculating the time complexity, if you see that you are going to get a time limit exceeded error, then you have to figure out some other optimal way, and that just takes practice. And at 1200 level, I would not say there are heavy usage of things like, yeah, and there is not heavy usage of algorithms. It is more like practice. Yeah, practice is the thing. Practice is the thing. Have you done all of the questions before going at to 1200? If you have solved 800, 900, 1000, 1100, and then you are moving on to 1200, that would be fine. But if you are directly jumping to 1200 and then expecting yourself to be able to come up with solutions, then I guess it would be a bit too optimistic. Yeah, that is cool. That is cool. That is cool. If you did all of them, that is cool. So now you just practice. Yeah, practice would be the thing. And also keep reading. Don't just keep solving questions. Also read about things that you do not know about. And that would be cool. I think you might have even seen some graph questions, some problems related to graph, maybe. And therefore, I would recommend reading some things from the Competitive Programmer's Handbook, like actually reading, not just saying out words, but actually reading, and it would be very helpful. That is like exactly just what I did. Just read through things and improve yourself. And now back to this thing. So we see that if we change our order of multiplying matrices, if we change that order, we can significantly improve the number of scalar multiplications that we have to do. So we have to figure out a way. And how we decide our order? We decide an order by parenthesizing a matrix. And what is parenthesizing a matrix? A parenthesized matrix, a fully parenthesized matrix, order of matrix is when you have a singular matrix that is being multiplied by a fully parenthesized matrix. Here we have a singular matrix multiplied by a singular matrix, and this matrix, which is singular, is multiplied by a fully parenthesized matrix, and then this matrix is multiplied by a fully parenthesized matrix. So this whole thing is fully parenthesized, and you can check all of these are also fully parenthesized. So that is cool. So that is how you define an order of multiplying matrices. And defining this order in different ways can change the number of scalar multiplications, and the number of scalar multiplications is going to be when you multiply two matrices of size ij and jk, the total number of scalar multiplications is going to be I into j into k, and we want to reduce, to minimize that total number of scalar multiplications. Yeah, so just keep at it, and because this is what this is what Tolstoy said. He said, every happy family is happy in a singular way, but every sad family is sad in their own way. So whatever bad thing is going on, because of which you are unable to solve 1200 rated problems, it is going to be very specific to you, to whatever mistake you are making, and I won't be able to guess it. So you just keep at it, and you will be able to figure it out. And yeah, and yeah, so for me, it is just solve questions, read, and then after reading a bunch, start solving questions again. That is what I figured out for myself. You can figure out some strategy for yourself, which is going to help you. We state that the matrix chain multiplication problem is as follows. Yep. Given a chain like this of n matrices, where I equals I1 to till n, matrix AI has dimensions p I minus 1. Okay, we are also given we have also been given a vector p, where the dimensions for AIth matrices are dimension pi minus 1 and pi. Why does this work? Because the last dimension, which represents the row, the number of columns for a matrix, is going to be equal to the number of rows of the next matrix, because only then can we multiply them, and otherwise we won't be able to multiply them. Fully parenthesize the product a1 to an in a way that minimizes the number of scalar multiplications. The input is the sequence of dimensions this. So we have been given an array. So we will look at that thing later. First, we will try to solve it on our own. The matrix chain multiplication problem does not entail actually multiplying matrices. The goal is to only determine an order for multiplying the matrices that has the lowest cost. Typically, the time invested in determining the optimal order is more than paid for by the time saved later on when actually performing the matrix multiplication. Because in the above example, the difference was a full order of magnitude. So in our example, we have been given an vector tmux set, tmux arrays, target USA, CD, concept, DP, matrix chain multiplication. Okay. So we will have a function which will return a long, which will be the minimum number of scalar multiplications that we have to perform. And the name of the function would be force matrix chain multiplication, and it will take in a vector of integers, and let's call it V, capital V, and that's it. Include vector and long, this initially 0, and after some point we will return the result. So what we have to do is, let's first of all write a recursive formula. What we have is a bunch of matrices, and this is very similar to the rod cutting problem. We have a bunch of matrices a1, a2, a3 dot till an, and we can put a bracket here and call this one parentheses and call this one another parentheses. And we will see what is the best optimal order for this part and what is the best optimal order for this part. And then we will move our bracket here and we will put these new brackets. Let's represent them with green. And then we will find the best optimal order for this part and the best optimal order for this part. And we will compare it with the last one, and what we'll just keep moving our vector, our placement of this breakpoint. We will keep moving it and we will return the one that is minimum. So that is simple enough. How is the recursive formula going to look like for this one? Recursive formula will find the minimum for something, minimum, where let's call this and this. Let's call this L and let's call this R. So we have to find the best optimal order for multiplying matrices from L till R. And we will begin our, let's say, our iterator. We will begin our iterator I from L plus 1. L plus 1. L plus 1. I will go from L plus 1 till it will go till this point and not past this point, because past this point would just mean the product of this whole thing, which doesn't make sense. Or yes, and both of these are inclusive. Our range is L and R. Both of these are inclusive. But what if we get something like L1 and R this? So I guess we will have to go till this point. Yep, we will have to go till this point. But when we are at this point, what do we do? When we are at this point, what is going to be the product? Because we cannot just call matrix chain multiplication for this whole thing, and this whole thing that wouldn't actually make sense. So we can say when our I iterator equals to some number, let's say R, which is in this case the right limit, this I think this starts inclusively from the left part, but till I it is not inclusive. So when we start from here, this so for our first part, left limit is L, but the right limit, and left limit is included, but the right limit, which is L plus 1, it is not inclusive. So we will only consider matrix 1, and we will keep increasing this part till it gets up to R, in which case we will have our limit equal to this thing. From L till R, L is inclusive, but R is not inclusive. And you can see that this thing is smaller than our original range, which was equal to L, R, both inclusive. And how is this thing LR smaller, greater than this thing LR? Because here, this is a rectangular bracket and this is also a rectangular bracket, which means L is included in both of these ranges. But on the right side here, we have a rectangular bracket, R is included, but here we have this parentheses. Therefore, R is not included. So this range subproblem size is smaller than this original problem size. So we are cool and we can move with that and write the solution. Let's do this. Okay, so we will also need L and int R. For int I equals L plus 1, I lower than equal to R, and I plus plus. And if at any case we have, if L equals R, the number of scalar multiplications is going to be 0 because we are not multiplying any matrix, right? Yep, because we are not multiplying any matrix. So response is initially equal to 0. And then we will start iterating. So res equals minimum, but shouldn't. We want res to be minimum. We will we would like to maximize res. Let's say in max, even though res is long. Okay, let's start my LSP. LSP start. You can see here I'm starting the LSP. LSP start line B. Now LSP is started and it is already giving me an error. I know why, because using name space std. Now the error is gone. Int 64. Okay, max. Okay, that is the only thing that I wanted to know from my LSP. I can turn it off. LSP is stop. Now it is better, and we are back to being amazing programmers who do not use LSPs. Now, internally, res is going to be minimum of original value of res and the number of scalar multiplications in the left part, which is going to be matrix chain multiplication for V, this matrix, and our left side is L and our right side is I minus 1, because right side is not included, because I is not included. It is going to be included in the uh, second half, the right half of the matrix, plus matrix chain multiplication for V matrix beginning from I going till R, and R here is included. And this thing plus when we get two matrices, let's say for our original matrix sequence, let's say we have a matrix sequence like this, and right now our I is at this location. So we multiplied these two matrices and we multiplied these two matrices. Now the total product is going to be product of these two new matrices. Let's call this A12 and A34. When we multiply these two matrices, then also we will have to perform some scalar multiplications for some time. And that cost of scalar multiplications is going to be V L minus 1 into V I into V R. And that is correct. Yes, that is how it is going to be. Why? Because for some matrix A I, if you want to know its number of rows and its number of columns, we can look in our V vector. Vi minus 1 is going to give us the number of rows in this ith matrix, and Vi is going to give us the number of columns in this matrix. And when we have multiplied a bunch of matrices, the dimensions of this matrix, since we multiplied starting from matrix I and we went till, in this particular example, let's say we multiplied from AL dot 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 till AI, and then on the right side we have some matrix. Wait, this is I minus 1, I minus 1, and is this AI minus 1? It from L till I minus 1, and then from I is going to the right side. I minus 1. But here we are taking VI. At the end we will have AR for sure, that is the right limit. The doubt, yes, the ith matrix is not included. Yeah, ith matrix is not included in the left part. It is included in the right part. Hmm. If that is the case, then a few things are going to be different. Yes, a few things are going to be different. Yes, shit. So what we should do is, yeah. Let's include this matrix, AI matrix in the left part, AI plus 1. This would be our right part and this would be our left part. And yeah, that would be cool. So in our matrix range of L and R, when we have I on the left part, we would have L included and I also included. And shit, again, if we go up till the right part so we don't have to go till the right part, we can go right -1 and we can begin solving from the left part. That makes sense. That makes a lot of sense. And we can say that our right matrix is going to be like this, where the left part is not included, but the right part is included. Then you will have to change a bit of multiplication here, and we cannot go equal to R because that will cause an infinite loop, and we do not like infinite. So this thing, this product and these product will give us a matrix. This one will give us a matrix whose number of rows is going to be VL minus 1, and the number of columns is going to be the number of columns in this matrix, which is VI. And in this, the number of rows, since this matrix is not included, the number of rows is going to be VI plus 1 because the next matrix I is not included, and -1 because we are finding the number of rows, which is just VI, and the number of columns is going to be VR. And if we are multiplying two matrices who have these dimensions, then the number of scalar multiplications for multiplying them is going to be this, multiplied by VI multiplied by VR. This is R, this is R, and this is V. So that is cool. What is the use of matrix chain multiplication? Use to reduce the total number of scalar multiplications that we have to perform while we are multiplying a chain of matrices. And your rating is 1600. You are like much better than me at this. So in this question, we have a bunch of matrices A1 to AN and till AN, A1, A2 till AN, and we can define, since matrix multiplication is associative, we can say first we are multiplying these two matrix, and then we are multiplying A2 with the product of these two, and then we are multiplying A1 with the whole product of these three, and that would give us a number of scalar multiplications that we would have to perform when we are doing something like this, multiplying them internally. And our goal, and they also give us an example which we can use to see, in which we see that changing up this order does change the number of multiplications that we have to do. So we have to find an order in which the number of these scalar multiplications is the least, and that is all we have to do. And that is cool. So this thing is going to be the product of the matrix that we get from the left side and the matrix that we get on the right side. That is what I have written here. Origin response plus the minimum number of scalar multiplications on the left side Where on second thoughts, left is going to be included, I is going to be included on the left side. And on the right side, we are not including I. We are going I plus 1, right? Yeah, makes. Does it make sense? Let's see. I mean, we will use some memoization in a while, but I think this makes sense. And also, I would like to tell you that Durgesh, you specifically, that I'm not using any LSP now, and I think that is cool. I am not using any LSP, so if I make a mistake, I do not get any errors. So I would have to keep in mind what I'm doing. Int main, let's define our vector and let's use this example that they have given us. They have three matrices of this size: 10, 100, 5, and 50. Vector of integers, let's call it V, 10, 100, 5, and 50. And int, or more like long, res is going to be matrix chain multiplication, and we will pass in V and also the starting and the end point. Starting is 0 and end point is going to be inclusive, so V dot size minus 5. See out the least number of scalar multiplications is this thing. Whatever it is res. CD concepts, DP and G++ matrix chain multiplication. Okay, shit. Yes, of course, because I haven't included the library. IO string and shit, it even suggests what I should do. G++ is cool. Okay, there is some error. Okay, we begin with L and R. Right, cool. L is included, R is not included. We call the function on this thing. L is 0 in the initial case and I is 0 in the initial case, cool. But in this case, we say I1 and R is size minus 1. Okay. Are we making the right choice at each step locally? And we are. We are making the right choice. We are not. We are not making the right choice. This L has to be 1 initially because our range starts from 1. Makes sense. Because at this step here, we are doing L minus 1 and 0 minus 1 is minus 1. That is not very good. 7,500, which is the correct answer. And the best answer is 7,500. So do they have some other examples? And I think they have some other examples. We will use them. They also have some recurrence formula here. A matrix like this. These are the dimensions. Let's use them. Here we have 6 matrices. First one 30, then 35, then 15, then 5, then 10, then 20, then 25. Okay, let's see what our program says. / out. It is 15,125. Is it correct? It is actually 15,125. So that is pretty cool. CLRS and Vim, good. Yep, CLRS is the amazing and Vim is amazing. Vim is amazing. Okay, so now we do know in the initial number of steps that we have to perform when we are doing some dynamic programming question. There were 4 things. We did characterize the structure of an optimal solution, what an optimal solution looks like, which is we keep moving our pointer. The optimal solution would involve the least number of scalar multiplications, where number of scalar multiplications of 2 matrices is defined by this thing, where the first matrix has dimensions ij and the second matrix has dimensions jk, and the total number of scalar multiplications is going to be I into j into k. And we want that to be minimum in our whole order of matrix, so that we defined our how our optimal solution would look like. And then we recursively defined, we didn't write an equation actually. We did try to write an equation. So let's say f v l r gives us the smallest least amount of scalar multiplications, where vi minus 1 and vi gives us the dimensions for the ith matrix. Vi minus 1 is the number of rows in this matrix, and Vi is the number of columns in this matrix. And so that is V, and L and R is the range in which we want to find the answer. And L and R both are inclusive. And this L is one indexed. We do not start from 0. Right? Remember that. So this function we can write it as, let's just represent it with f. We can say when it is equal to 0 when L equals R. Since this is inclusive, L equals R would mean we have only one matrix. When we do not have anything to multiply this with, then we do not perform any scalar multiplications. And that is what we say here. If L equals R, return 0. That is cool. But if L is not equal to R, then find the minimum of f v. We will start iterating fvl I plus f v, and this is like amazing writing, I plus 1 till r plus it would be plus v I minus 1 into v l minus 1, my bad, into vi into v r. And yep, if they are not equal to 0, where I ranges from L to R minus 1. Yep. And what is this part? What the heck is this? What is this thing? This thing is, since our L is not equal to R, it would mean we have some matrices A L plus 1 dot 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 till A R. We have a bunch of matrices. So we could say we are initializing a iterator I which goes from L till R minus 1, and it starts from L, and wherever our iterator is pointing to, we will put a opening and a closing. I said them the wrong way. Closing and an opening bracket at that point to the right of this ith matrix, and we would find what is the best scalar multiplication if we bifurcate this matrix in this order, in this way. And so we can put a bracket here, and this is what we will get. And then we will get a matrix from this left side. Let's call it A capital L, and we will get a matrix from this right side, which is capital R. And the number of scalar multiplications performed in this part, left part, is represented by this thing, function called giving V, the number of which stores the dimensions of the matrices, starting from L going till R, going till I. I is included in the left part, and on the right part, this the scalar number of scalar multiplications on the right part is called to the same function f with V given, and I is not included, so we go from I plus 1 till R. R is included on the right side. So this would return us, give us two matrices, AL and AR. And then we would have to multiply these two. And since we know the dimensions of this thing, we began from L. The dimensions for this thing, the number of rows in this matrix would be VL minus 1, because the number of rows in this final matrix is going to be the number of rows in the leftmost matrix, and the number of columns in this is going to be the number of columns in the rightmost matrix, which is I. AI, since I is included, therefore it is the rightmost matrix in the left part, and the number of rows, the number of columns in that matrix is VL. So this matrix VL is going to have these dimensions, and this matrix AR, since it is the product of all these matrices which start from A I plus 1 dot 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 till AR, the number of rows in this matrix is going to be the number of rows in the leftmost matrix, and the number of columns in this matrix is going to be the number of columns in the rightmost matrix. So the number of rows is going to be V I plus 1 minus 1 plus 1 minus 1, because plus 1 is the I plus 1 is the matrix, and to get the number of columns, the number of rows in a particular matrix, we do the number of matrix minus 1. Here here is the same thing, we are doing the same thing, the number of the matrix, the number for that matrix minus 1, which is just vi vi remove all of that, remove. And then the number of columns is going to be the number of columns in the rightmost matrix, which is, this is A, that is upside down V, which is VR. And when we multiply these two matrices, the number of scalar multiplications involved is going to be VL minus 1 into VI into VR, and that is cool. So we first multiply the left part, then the right part, and then the matrices that we get from multiplying the left part and the right part, and this will be the number of scalar multiplications performed when multiplying those left and right parts, which is represented by this number V L minus 1 into Vi, this is I, Vi, and then into VR, and that is what we do here. Call the function matrix chain multiplication. That is a too long name. That name is too long. From V beginning from L till I, because I is included in the left part, and then for the right part, call the function again on I plus 1 till R, and then the number of scalar multiplications we get when we multiply the left part with the right part, and we are taking the minimum over all i's, and that is cool. That works. And yeah, so that does work, but the problem is we have to figure out Our function is not recursive. Our function is not recursive. Our function is bad. So what we can do actually, or what we would like to do, is have some memoization. And we can say that whenever we are calling this, we are changing the left side and also we are changing the right side. So there are some variations that we can do here. This is recursive and without memoization, which is like the worst thing. Recursive is not as good as iterative solution. And second of all, we are not even using memoization. Let's first of all use memoization. So map, we will have to use a pair. I think pair is in the utility thing, utility.h map pair, and uh, we are using a pair as the key because we have two things here. A solution to a particular thing only depends on the left and the right limit, and it will point to its answer. We will call it memo. So if memo.count for L comma R, we already have the answer for LR, then return memo L comma R. Otherwise, if that is not the case, before returning, put it into the memo L comma R equals rest and then return. So now at least we have a bit of memoization. I hope we don't get any error. Utility.h is not a thing. I guess it is just utility then. Yep, it is just utility. And the answer is correct. And we are also using memoization. Now, what I would like to do before getting on to finding what the optimal solution is, since there are a couple of ways for writing dynamic programming solutions for dynamic programming, there is recursion. Okay, let me not write it down, but actually use text. For DP, we have two methods. First is recursion with memoization, and the second is iteration with tabulation, and that is cool. We have written this thing. We want to write, we also want to write this thing just for practice. And also in both of these things, okay, let me use arrows. In both of these things, okay, we can use a better arrow than this. Yo, that is cool. See, that is cool. That is cool. That is what comes with the Excalibur. And in both of these, finding solution is also one thing that we have to do, because what we have written, it just gives us what the what the value that the optimal solution returns would be. But what is the optimal solution itself, that we do not know, and our solution does not return to us that thing. So we have to write something which will keep track of some extra information which we can use afterwards to find the optimal solution. And I am thinking of vector int, let's say a vector of integer which remembers where we are putting those brackets. So let's call it cuts. I think that is very reasonable. And its size is going to be equal to v dot size 0. And that is Not very good, I think, because what would a cut depend on? It doesn't depend on this thing. Yeah. Shit, a cut doesn't depend on this thing. I guess we will need some two-dimensional thing and not this. Yeah, we would need something that is two-dimensional. But can we avoid it? Can we avoid using some two-dimensional vector? I mean, we should not use it. I think we can avoid using two-dimensional vector if we use iteration. But when we are using recursion, we have to use it. We have to be two-dimensional when we are using recursion. And what are going to be the dimensions? The dimensions are going to be square. Yeah, the dimensions are going to be v size. And for these, we will have a vector of integers whose size is v dot size. That is cool. That work. And yeah, and no, we cannot use new. We can use NW. It equals this thing. Now, if NW is smaller than our response, then first of all, response becomes equal to NW, and also we will put this into this. But sometimes we are actually not going inside. So is that bad? I think no, because we are only avoiding going inside this loop when we have already found this. And when we did find this for the first time, we would have updated our cuts. So that is cool. I think we can avoid using this two-dimensionally. We can update cuts. No. Yes, ship. Yes, 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 yes. Okay, I am stupid. We can avoid making this two-dimensional. Cut I, cut I, cut I gives us says that when we have a matrix of size from 1 initially, the first matrix till I, where 1 and I are included, where is the point where we should make the cut in this range 1 to I, and 1 and I are inclusive. In this range, where should we make the cut? That is what cut I is going to return. So that works. That works. That works. If that is if the current one is better than the last one wasn't even anything. Last one is infinity. Last one was infinity. So in that case, since our range is till R, we can say cuts R equals I, where I is the left part, where I, what we get, let's say we get out of this X. X would mean that this matrix of range 1 to I, we have to divide this matrix into two ranges, 1 to X, where X is included in the left part and X is not included in the right part, but I is. So this thing, cut I equals X, would mean we are cutting up this matrix from 1 to I in this manner. and that is cool. X is included in the left part, but not in the right part. So when we have this information, we would like a function which returns the vector, and let's call it make solution, and it doesn't even do anything. It will internally create a vector and shit. We should make this a reference. It will internally create a vector, and the size of the vector, what is it going to be? And how are we going to represent the solution? Since let's say we have three matrices, A1, A2, A3. Here I know for sure I will have an opening bracket. Here I know for sure that I will have a closing bracket. I don't know for here and for here what kind of things I have. Okay, this will also be a recursive call, by the way. Yep. When I go to this length from 1 to the whole size of the matrix, let's call this S, and I see that it says 2. That would mean I divide the matrix about at this point. So I can say, I can put a left bracket and then whatever this thing returns, and then put a right closing bracket and then a opening bracket, and whatever this thing returns, and then a closing bracket. And whatever this thing returns is a recursive call to that function. Therefore, it should return a string and not this. And no, a reference is not good because the string is going to be on the stack. String res. And what do we have? Yep. What is our range? That is a nice question. Cuts. Cuts is a global variable. We don't need it. Left and int r. Shit. If that is the game that we are playing, then it is messed up. Then it is messed up. Shit. We do need a two-dimensional vector here. We do need a two-dimensional vector here. My bad, my total bad. Shit. And this is initialized in two-dimensional way, so that is cool. And yep, this is neovim, and this is not neovim. This text editor is neovim, and what we are trying to do is in competitive programming or in algorithms, there is this method called dynamic programming, and we can use this method. This method is very powerful. We can use this method to solve a bunch of problems. And here what I'm trying to do is we are going through this chapter in this book. This book is called CLRS book, clrs.pdf, here, right here. And we are practicing this method of solving algorithmic questions. Because if we can do this, if we get very good at this method, we will be able to solve a lot of problems. And we will become really good human beings. People will start to respect us, and that is good. Respect is good. So yesterday we went through this first part, which was about rod cutting problem. And right now we are going through this part, which is matrix chain multiplication. And presently I went through and explained what the problem is. And then I wrote a solution for the problem. This thing does solve the problem, but what we want to find out is a way of finding out, okay, what kind of problems does this solve? That is a nice thing. Yep, in a minute, we are solving optimization problems, and that is optimization. And our current solution is only giving the value that we get when we solve the problem in an optimal way. But we want another information, and that is the solution itself, the solution which is giving this optimal value. And that is what we are trying to find out here. And we need some extra information about cuts. And what will cuts give? Now, since cuts is two-dimensional, so cuts I bracket j, this thing will say when I have a matrix of range I to j, I and j inclusive, what is the best place to make a cut x? This will give me x. When the range of my matrix is ij is inclusive, and that would mean that I divide my matrix in two things. X is included in the left part, and on the right we will have x to j, and j is included in the right part, right? Cuts ij would mean that I divide this matrix I to j in two parts. From I to x, x is included in the left part, but x is not included in the right part, hence the opening bracket there. And we would have to change this thing too. We can just say ij, or since we have L and R here, so cuts LR equals I, because I is the place which is giving us the best cutting position in this submatrix of size LR. So I think that is cool. That is cool. And then we will find C, which is like cut. We will cut this range LR at this location C. And we will also like to have a base case. Yep. If L equals R, return. And how are we going to represent our matrix? We will represent it with numbers. No, no, no. We will represent it, return, with index, with A plus L. No, not A plus L, A plus L, A plus L. A plus 0. Yeah, A plus L, A plus L, because L is the index of this singular matrix. And what we would like to have is when we are multiplying A1, A2, A2, and A3 in our solution itself, since I don't know how we can put subscript in terminal, we will represent this like this: A1, A2, A3, or a better solution would be A subscript 1, A this underscore 2, and A underscore 3, and we can have brackets like this. Yeah, that is cool. That is cool. That is cool. That is cool. And I think, yeah, internally also I will have brackets, but what the heck is this then? Yes, then I will also have a bracket here. That would make sense. But isn't this like too many brackets? So if this internal function just returns AI and I put only a left bracket and a right bracket, I would have A1, A2, left bracket, right bracket, then left bracket, A3, and right bracket. This looks much cleaner than this. That is also tilted. So that is cool. Okay. If L equals R, we are at a singular matrix. So our string or return A subscript plus L. And this will return us a singular thing. And then if that is not the case, then our result would be somewhat like left bracket. Yeah, initially it is just a left bracket. And then we will add res plus equals make solution for the left side. And the left side will begin from L and go till C, right? And then res plus equals, we will add a left bracket and a right bracket plus make solution for the right side, which is going to involve C plus 1 till R, the ending. That is cool. And then finally, a closing bracket. And then return that. And we don't even have to write this in two separate lines. A single line will work. We can say this like right here, string res equals, or make this look more complicated like this. And on the left, we will have this. That should work, right? Make solution. Wait. Left bracket. A left bracket make solution for the left part, then left bracket closes, then a right bracket, right opening bracket, make solution for the right part, and then that thing also closes, and then return. That actually looks pretty cool. I think that will work. I think that will work. Make solution beginning from left will begin from 1, and it will go till v dot size minus 1. And I hope it works in first try. If it does, it will be cool. Is it going to work? Is it going to work? It is indexing L and R, and internally it is only indexing values which we put in. Yeah, put in. Okay, I think that is cool. G++ at least compiles. It does compile at least. Hmm. 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 I guess that is because when this is the case, we have to update. Makes sense. When this is the case, cuts, or we can fill cuts initially. Yeah. Return 0. Initially, when we reassign cut, here we can say for every value, no, we can do this here. Return 0, but before that, put cuts I, j equals LR. LR equals R. Does not matter because L and R both are same. We can put anything. That is also not good. That is also not good. Not good. At least we will have a new line and not this percentage sign. Okay, so we have some problems that we have to fix. Bro, are you working somewhere? Nope, I'm not working. I'm not using any LSP right now. Yeah, I'm writing without any LSP because I'm on a Mac and I'm using G++, which is GNU compiler, and it does not talk well to uh, the GNU libraries, which I am using with my compiler, and the LSP is ClangD, which is by Clang. So they do not they are not very good friends. So therefore, I'm working without any LSPs for C++ specifically. And if you want the config, it is at my GitHub repo, nvim rc. There, you can go there, and there is my whole config, and that is like nice. It also has my boilerplates for C++ competitive programming. And yep, back to this thing. We haven't even begun reading the question. Yeah, vector int v. So this thing is not making the solution correctly. I think the problem might be with this part. If I do 0 plus, I think now maybe. Okay, that is not the right thing. That is scalar. That is totally messed up. Okay, let's use a smaller example before this. Initially, the other example was 50, 100, 5, and 10, or maybe I guess it was more like 10, 100, 50, and 5, or 5 and 50. Yeah, 5 and 50. I think this was the initial example. And yep, backslash, backslash, and backslash, and twice G++, let's see, and 75,000 and S size, call size. Something very bad is happening. Return, okay, that is very good. That is very good. I think it was because this thing which we were returning was being returned from the stack. Ah, yeah, shit, I messed up. I messed up. Yeah, and now I get my mistake. It was being returned from the stack, and stack was getting overwritten by crazy stuff. And again, yeah, 0, 0. I hope it works. It does not work. Okay. String s initially a underscore s plus equals 0. Okay, I want to test something. If I add a character to a string, what do I get? Will I get a0 there? I do not actually. If I add a string to that, I do not, because I have to return the goddamn string. Okay, now a0 is working. But if I add a character, what happens then? Okay, character is also working. So if I increase the value for this character by L amount, yes. That makes so much sense. Okay. Since that L and R could have multiple digits, then doing 0 plus L and R is not pretty cool. So let's have a string stream SS, and we will say SS takes a underscore takes in L, and that is it. And we will have SS dot stir. I think that is the function, but we also have to include the library. Okay, let's start LSPI because I don't know the libraries. Lang D, include string stream. String stream SS. LSP restart. Okay, now it is better. It's giving me error here. File not found. Why? String.h. Shit, yes. LSP is hallucinating officially. Shit, it seems to be fine now. It seems to be like absolutely fine now. It might actually like still mess up if this thing, the thing that is returned from the stack. So it might still, yeah, LSP is not giving any errors. Line D, LSP is not giving any errors. Voila, it works. Cool. So we can construct a solution, we can find the solution. Mhm. Minimum number of scalar multiplications is res. And yeah, so minimum number of scalar multiplications is this thing, and the way that you multiply them is in this manner. That is cool. And you mean competitive programming by that, I suppose. I hope you mean competitive programming by CP. So we also had another example which was more complicated. Let's run our new code with that one, this one, which was a bit longer. And it has 30, 35, 15, 5, 10, 20, 25. It, that took me too long to write. That took me too long. It shouldn't have been that long. What the heck? Okay. 30, 35, 15, 5, 10, 20, 20, 25. That was a bit faster than before, but still it is not up to the mark. G++. Okay, it is working. G++. Yeah. Let's give a new extra line. New line, new line. Yep, that is correct. I guess that is correct. Giving a bit of space, would it be nice? Would it be nice by giving a bit of space? This is fine. This is between these brackets, I guess. Let's see. That is nicer. How's that? That is a bit wrong because of this. It is just this same thing expanded. Anyways, so we have written our recursive solution, recursive solution, and yeah, this part, this part. We have written our recursion with memoization, and we have also done this thing, finding the solution using recursive part. What we have to do is using iteration with tabulation. And this writing this part is a bit more complicated than this part because we have to find the dimensions of the table that is going to be later. But this part is, I would say, relatively simpler than recursion, finding the solution part in tabulation method. Anyways, let's rename this to recursion, and also this to recursion, recursion, and recursion. Let's write another one which returns a long matrix chain multiplication iteration. It takes in a vector of integers v, and that is it. That is it. That is all it takes. And we will have a vector two-dimensional which will store integers, and we will call it res or tab, as in like tabulation. We also need to give it dimensions. V dot size, the size of the outer vector, and the internal vector of integers will also have the same size. Will it? Yes, it will. It will, because size of this thing V is one greater than the number of matrices that we have. That is Cool. And what would tab ij give us? Tab ij. Wait. Yeah. How old are you? Are you in high school? Nope. I am in college. So I mean, cost price. That is also you, which something that you could have meant. My bad. I'm thinking of bad things. And my laptop is going to die. Okay, its life is saved. Now it is not going to die. And now what we have to do is write solution with iteration, iterative solution, not solution, but find the value using iteration and then find the solution which gives that value. And for that, we will store some extra information while iteration. So we will have this thing. And what will tab I j give us? Tab ij will give us tab ij. Tab ij will give us the minimum number of cost, the minimum cost of multiplying these two matrices. The minimum number of scalar multiplications we need to perform when our matrix range is tab ij and both I and j are included. So we will do our same routine. We will have some iterator, let's say k. We will go from I till j minus 1. And at each iteration, our range would be I till k, where k is included, but k is included in the left part, but in the right part, we do not have it included. J is included on the right part, of course, because it is on the right. And these two multiplication matrices, then we will multiply whatever we get from this, and that would be our answer, and we will compare it with the current value of tab, and that is cool. But you also need to initialize some values. So for int I equals 0, I less than v dot size I plus plus, we will say tab I equals 0. I mean, everything is 0, so we don't have to do it as shit. And we will increase our range int I equals 1, I less than v dot size I plus plus, and internally hmm, hmm, hmm. In iteration, if this means this, then our final answer would be tab 1. This is 1. No, that is not 1. That does not even look like a 1. Tab 1 till, there is no need for a comma here. Tab 1 till the last size of this matrix, the number of matrices, this thing, that is what we are after. So let's say every time our iteration will begin from 1, and what we are increasing is this number. Every part, for every iteration, we will start moving from 1, and first time we will only go to right by one number, then we will increase our length to be equal to 2. When L, our length, equals 2, then we will start iterating from 1 and we will go till 2. That is a huge improvement. And when L equals 3, we will go from 1 to 2 to 3. And whenever we are finding some answer for, of course, we would be calling internally something else also. That makes sense. That makes sense. So when our length, let's say, equals 1, when our length equals 1, we will have one iterator on the left and one iterator, let's say j, on the right, and their distance is always going to be equal to the length. So initially we can say length is 1, length minus 1, length minus 1. So initially they both of them will point. Let's say we have one a1, a2, a3, a4. When L equals 1 in our first iteration, which we are going to represent with the green color somehow, initially I will point here and J will point here. Then both of them will move one step. I will point here, J will point here, and boom, boom, boom. We will keep moving forward, and we would have filled the matrix tab, that is tab, for every value I, J, where J minus I minus 1, J minus I minus 1, J minus I plus 1 equals 1 L. And when L equals 2, which we are going to represent with blue due to some reason, when L equals 2, my laptop should be charging, my it is not charging though. Hello. And bro, do you have any list of problems? By using that, I cover all patterns. How, which pattern? Basically, DSA problems related to that pattern. Based on particular pattern, that means by solving those problems, we can solve all all problems. You need to develop concepts, frameworks, which you can apply on problems. And to develop those frameworks, you can, this is the sheet that I am following, CP31. You can follow this thing, and this seems to be pretty cool. You can solve problems from this and develop patterns in your brain, which will help you solve problems. But also, I'm saying that solving these problems is not going to be enough. You will have to read quite a bit, like right now. Okay, so that seems cool. We will have a length which is increasing and cool. So let's say length, 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 and internally for int I equals 1, we will start iterating from 1, and while I plus 1, I, I minus 1, or I plus L, I plus L minus 1. Yes, I plus L minus 1, I plus L minus 1, because I is included and L is the total length. So we do not want to increase it. Yeah. So L minus 1 is the number of elements that are going to be on the right. So this thing gives us the index of the right range. So right range, while it is lower than v dot size, I plus plus. So what we do in this range, shit, we would need another loop internally. That is like n cube. That seems to be very bad. That actually seems to be very bad. But that is necessary. That is necessary. We cannot do it without this. So our range is from I to I plus L minus 1, where I plus L minus 1 is included. So we will have, let's say, k equals I initially, and k less than I, less than equal to I, because that is included, but less than because we do not want to k go up to that element. So I plus L minus 1 and k plus plus. What we'll see is first we will initialize the solution to some very, very big value. Yeah, we will initialize it to some very big value, and that infinity? No, no, not infinity, because if we do that, no, not infinity, because length 2, that is fine. Now we can go up to infinity. Yeah, now we can put it equal to infinity. So tab I j. What is j? J is nothing. I plus L minus 1 equals int 64. That is not 64. This is 64. Max. And we can also fill tab, not tab. This are cut thing which we need to write solution later. So let's say n or long nw new solution is the left part, answer for the left part, which is going to be tab starting from I going till k plus tab k plus 1 till I plus L minus 1 plus, now is the funny part, I minus 1 into v, I minus 1 is correct, into v, I minus 1 is correct, actually correct, into v k into v I plus L minus 1. Now, if NW is smaller than what has been, which is tab, it's not tab, which is tab, I plus L minus 1. If that is the case, then update the value for this current thing is going to be NW and put it into cuts. Cuts I, J. G is nothing. L minus 1 is K. Make a cut at this place. And if this works, going to be cool. Chain multiplication, ratio, iteration, and it doesn't need all of these stupid things. It just needs M, V. Hopefully it at least compiles. It does not compile, okay. Int 64 max, which makes sense. C limits, we do not have C limits, and we supposedly have some extra parentheses, not parentheses, but this thing. This one corresponds to that, this one corresponds to that, and this one corresponds to that. All of them are correct, but we need C limits. So what were we doing there? Didn't we need C limits for that? I guess not. I think it also has dot edge. No, it doesn't have h dot edge. No return statement. Ah, shit. Makes sense. Makes sense. We are not returning anything. Return tab beginning from 1 going up till v dot size minus 1, which could have been written as dot back, the last thing in this one, starting from 1, the last value. it does compile at least, and we do get the correct answer. We do get the correct answer, which is 1500, 125. And is this thing also the same? We can check. We can check. After assigning, let's recall the function, and we will say this equals matrix chain multiplication recursion with v, and starting at 1 and going to v dot size minus 1. Also, after this cuts C out or put char 10 twice. Shit. G++ and dot slash out. And do we get the same thing? A1, A2, A3. Yeah, we are getting answer the same. Answer is the same. Numerical value is the same. And internally also, the bracket placement is also the same. So that does work. Which site was that? Which had separate topic-wise problems you were solving? That was yo. Yep, DP practice is nice. Like it will make you stronger. Strong. It was this one, CACS. Competent. I don't know the full form for this. Introduction. What is the full form? Collection. It is conglomerate. Something. I don't know the full form of CSES. And they are this. This is not a. This is a project which is run by a single individual, and his name is Antti Laksonen. This guy, and he has this. I don't know which one of them is the real person we are looking for, but yeah, he is the person who wrote Competitive Programmer's Handbook. Antti Laksonen. He's from Finland, Helsinki, and this is the website. CSES full form. What is it? Code Submission Evaluation System. Okay, CSE is code submission evaluation system. So what you have to do is go to code submission evaluation system, and that's the one. Yep, that is the one. I just practice with ICPC prelim DP problems. Huh. I for me, just solving problems does not help me as much. I like to read and then form some opinions. Here I read about the problem statement and then I solved the thing. But this is not the first time that I'm solving this particular problem. I have read this chapter before, and now this was cool. I solved this problem first of all, like this DP using recursion with memoization, and then I also kept extra information so that I can find the solution, which gave me the optimal value, and then I implemented the same solution with iteration with tabulation, and that also gives me the solution and not just the optimal value. So that is cool. And yeah, I like to read. I like solving problems does not help me particularly as much, and reading also helps a lot. Reading about things and making opinions and frameworks. ICBC 23, Spark prelims. I'll see if I can find it. We'll see if I can find it. How do you remember that there was this problem in that particular year in prelims or something like that? That is cool that you can remember that. That is like Magnus Carlsen. Oh, that is the game between Mikhail Tal and Bobby Fischer in the year 1954, something like that. That is a cool ability, good memory. Okay, so before going on to our quest for writing the whole, okay, should not use mouse with Neovim. That is illegal, and that is like people who use mouse with Vim, they go to hell, I've heard. They don't even go to shit. Is it what is the place where you go to before you either go to hell or go to heaven? Uh, you go before heaven. Purgatory, something like that. Purgatory, purgatory, the state of purgatory. There is where you will go. You don't even, you won't even go to purgatory. You will go straight up to hell if you use mouse with Newgem. So don't use mouse with Newgem. That is bad. Memoization or underworld shit. Uh, Tabulation is faster, but it is harder to implement. And I mean, yeah. Wait. Are you asking between recursion and iteration? No, you are asking between memoization and tabulation. So they are fine. They are both the same. I mean, if you are using here for memoization, I was using a map, this map right here, map from a pair of integers to an integer. I could instead say a vector of integers and use that. Now both the things are equivalent. I just have to change this thing. I just have to say if memo ij, if memo ij, then return memo ij, memo, wait, ij are nothing. We have L and R as our variables. L and R, and internally also just memo L R equals rest. So now they have the same time complexity, and I hope it works, and I think it will work. Or maybe not, or maybe not. Vector, because it does not have a size. That is a good point you have there. After initializing vector, I can say memo dot, wait, I'm assigning here. Again, yes, because yeah, I was doing something else. Here I can say memo assign this thing. Yep. Now for both memoization and tabulation, the time is same because the data underlying data structure is vector in both the cases. Here in memoization, I'm using a two-dimensional vector, and also in tabulation, I'm using a two-dimensional vector. But the real question is between which is faster, recursion or iteration. Tabulation is better memorized because we can store only last two values, while in memo, we store all values. I mean, look at this. Store last two values, while in memo, we store all values. No, well, in this case, I when we are cutting down on like in coin change problem, we can change our two-dimensional vector into a one-dimensional vector, right? When in coin change, we can do that because answer for some particular cell, let's say here, depends only on like if we are finding answer for this particular cell here in coin change problem, the answer only depends on some values in this singular column and not on any other column. So we can collapse this whole two-dimensional vector into a singular dimension and use that. And I think that is what you are referring to when you are saying is we don't have to store all values. I saw a video in which he told something like that, but times both are same. I mean, it depends on the data structure, underlying data structure that you are using. In this case, in this particular case, we are using a two-dimensional vector where the time is same, and yeah, where the time is same. So that is cool. Time is just same. The real question is between recursion or iteration. And recursion is slower, iteration is a bit faster because of less overhead and function calls. Counting the number of parentheses, yes, that is where we have to begin. And it has already been 2 hours and 10 minutes, and I haven't actually, well, I haven't read, but I have written the code for the whole thing, which is nice. And without without LSP, that is cool. Not using an LSP. Before solving the matrix chain multiplication problem by dynamic programming, let us convince ourselves that exhaustively checking all possible parenthesization is not an efficient algorithm. That is true. Let's say we have n number of matrices. So how many ways are there in which we can parenthesize n matrices? That is a nice question. Let's say when we have a singular matrix, we have one opening and one closing parentheses. When we have two matrix, we have one opening, one closing. This is A1, one opening, one closing for this, and then one for both of these. So in this we had let's just count the number of opening parentheses. Here we had one, and here we have one, two, and three. Three in total. And when we have three matrices, A1, A2, A3, how many do we have? One, two, three, four, somewhere in between five. So five, it is being increased by two. So we can say n, fn, let's fn represent. When we have n number of matrices, then we will have 1 plus n minus 1 into 2, I guess. Number of opening brackets, because here we had 2, here we had 3 brackets, and we can see whenever we are adding a new matrix, we are adding one bracket here, and let's say we multiply that matrix with the matrix that is to the left of it. So we added one bracket for that. So in total, we added two brackets, and that is cool. So in total, for a matrix, for a sequence of n matrices, we have n plus n minus 1 into 2, which is, wait, which is just 2n minus 1. Yeah, 2n minus 1 brackets, 2n minus 1 opening brackets, and therefore subsequently 2n minus 1 closing brackets. And we know when we have n brackets, how many ways are there to arrange these n brackets? Those are called Catalan numbers. And Catalan numbers for 1 is 1. C2, when we have two brackets, there is this way and there is this way. So there are in total two ways. And Catalan number for 3 is 1, 2, 1, 2, 1, 2, 2. And 4, no, 2, 1, 5. In total, we have 5 ways to arrange three brackets, which are these. Are there any other ways? I don't think so. That is it for 3. But the point is, this is a lot of numbers, and there is actually a formula for Cn equals 1 by n plus 1 into 2n factorial 2n n. This is like 2n choose n. This is the formula for the nth Catalan numbers, and if this is our number of brackets, then there would be 2n bracket 4n minus 2 4n minus 2, and below we will have 2n minus 1. This is the possible number of arrangements we could have, and this is a very big number. This is a very big number. We do not want to calculate this many things, so we do not do that. Of course, recursion is slow. We have to solve for the already visited values. No. We can avoid that if we are using memoization. We do not have to solve the same thing again and again if we are using memoization. So recursion is not slow because of the fact that we are solving the same problems again and again, because we are not solving the same problems again and again if we have memoization. Recursion is slow because we are calling another function. Look at this. Here in the tabular method, when we are calculating the new value, we are here getting value from some, we are here getting value for this smaller subproblem by just going to a table, and here also we are getting value for a smaller subproblem by going to a table. But in recursion, when we are getting the new answer, we are calling a function, and calling a function is slower than calling a function is slower than getting into some values. You know, calling a function is slower than accessing some value in a matrix. So that is why recursion is slow, not because we are recalculating something that we already calculated. And yeah, efficient algorithm denote the number of alternative parentheses by a of a sequence of n matrices by Pn when n equals 1. The sequence consists of just one matrix, and therefore there is only one way to fully parenthesize the matrix product. And there is only one way to fully parenthesize the matrix product. When we have only one matrix, cool, makes sense. And therefore there is only one way to fully parenthesize the matrix of one product when n equals or is greater than 2. A fully parenthesized matrix product is the product of two fully parenthesized matrix products and subproducts, and split between the two products may occur between the kth element for any k makes sense. So number of ways for p is pk and pn minus k makes sense. K is going from 1 till n minus 1. We have written a recursive formula, and this kind of like the answer to that. These are the Catalan numbers. This recursive formula is for Catalan numbers. Yep. A simpler exercise this shows that the solution to recursion, this thing, is 2 power n. The number of solution is this exponential, and brute forcing is going to be very bad. We do not want to do brute force on this massive number. Therefore, we need an optimal dynamic programming approach, which involves 4 steps. Characterize the structure of an optimal solution, write how an optimal solution would look like, recursively define the value of an optimal solution. Yes, that is if you have solution to smaller subproblems are smaller, optimal solution to subproblems, then how you could leverage that fact and find answer to a bigger level problem. then compute the value of an optimal solution. Yeah, compute the value of an optimal solution. You are just computing the value of an optimal solution and not the optimal solution itself. So let's go through step one. What an optimal solution would look like. In the first step of the dynamic programming method, you find the optimal substructure. Okay. Then you use it to construct an optimal solution. Uh-huh. And you, I mean, one viewer word that is, look at this. There is this movie, Martyrs, which came out in 2008. French movie, and do not look it up. I'm just going to say that, do not look it up. To perform this step for the matrix chain multiplication problem, it is convenient to first introduce some notation. That is very nice of you. Aij, where I lower than equal to j, denote the matrix that results from evaluating the products starting from j, from I till j, and I and j both are included. Okay, and denote the matrix. Okay, it denotes the matrix that we get when we multiply all of these, or don't, when I equals to j. It is a singular matrix. If the problem is non-trivial, that is I is lower than j, then there must be a split. Then to parenthesize the product from I1 to j, the product must split between ak and ak plus 1. Ak would be included with I, the left part, and ak plus 1 would be included with j, the right part. For some integer k in the range, yep, k will go from I till j. I'm like very happy because this is exactly what I have written here. So that is pretty cool. That is, for some value of k, first compute the matrices ai till k and a k plus 1 till j. That is exactly what we wrote here. We are taking k inclusively with the left part and k exclusively with the right part. We are not including k on the right part. Therefore, we are starting the right thing from k plus 1. That is cool. And then multiply them together to produce the final product of this thing, which is going to be v, or yeah, vi minus 1 into vk into vj. Somewhere they must have written that also. The cost of parenthesizing this way is the cost of computing the matrix ai plus the cost of the computing the right side of that matrix, which is ak plus 1 till j, plus the cost of multiplying those resulting matrices together. The optimal substructure of this problem is as follows. Suppose to optimally parenthesize a1 ai till aj, you split the product between at this point k from ai till ak, and on the right side we have from a k plus 1 till aj. Then the way, and k starts from I and goes till 1 minus j. Then the way you parenthesize the prefix subchain, this within this parenthesization of a1 to j must be an optimal parenthesization of a1 to ak. Why? Why is a good question? Why is actually a good question? Why that would be? Why is a genuine question? If there were less costly ways to parenthesize AI and AK, then you could substitute the parenthesization in the optimal parenthesization of AIJ to produce another way to parenthesize a from I till J, and that would be a lower, that would have a lower cost than the way that you are doing it right now. So by contradiction, this is proved. That is a very nice method. By contradiction, why should it be optimal? Because if it wasn't, then our overall answer won't be optimal. So by contradiction, we need the subproblems to have optimal answers. That is cool. A similar observation holds for how to parenthesize the subchain. This thing, yeah. By contradiction, we can say the right side should also be optimized. Now let's use the optimal structure, substructure, to show how to construct an optimal solution to the problem from optimal solutions to subproblems. Yeah. How do we construct optimal solution to a problem when we have optimal solutions to subproblems? Any solution to a non-trivial instance of the matrix chain multiplication problem requires splitting the product, and uh, any solution to a non-trivial case of the matrix chain multiplication problem requires splitting the product, and any optimal solution contains within it optimal solutions to subproblem instances. Yep. Why? Because we proved it here with contradiction. That is good. Thus, to build an optimal solution to an instance of the matrix chain multiplication, split the problem into two subproblems from ai till ak and ak plus 1 till aj. And yeah, where k will range from I till j minus 1. Find optimal solutions to the two subproblem instances and then combine these optimal subproblem solutions to ensure that you have examined the optimal split. You must consider, yes, to examine the optimal split, I must consider all the ways of splitting this problem into two subproblems. That is cool. That makes sense. And also, yeah, I mean, that makes sense. And also, I would like you to just user concern. Do not look up this movie, Martyrs. This is a French movie. Do not look it up. It was released in 2008. Just do not look it up. I think I've said that twice now. A recursive solution. Now, the next step is to define the cost of an optimal solution recursively in the terms of the optimal solution to subproblems. Yes. How do we define our solution recursively? In terms of optimal solutions to subproblems. For the matrix chain multiplication problem, subproblem is to determine the minimum cost of parenthesizing some subpart of that whole matrix when we are splitting this whole matrix at some index k. Given the input dimensions this, an index pair ij specifies a subproblem. Let mij be the minimum number of scalar multiplications needed to compute matrix aij. For the full subproblem, the lowest cost way to compute a1 till en is thus m1n, and that is absolutely cool because that is exactly what we did here. Tab 1 dot back. Back is the last value. Tab 1 means the starting value. From starting from part 1 going till the end. M1n is equivalent to tab 1 dot back. So that is cool. We can define mij recursively as follows. If I equals say the problem is trivial, answer is 0. The chain of costs, the chain consists of just one matrix aii. It is ai. So that no scalar multiplications are necessary to compute the product. This mii equals 0 because we didn't multiply anything. To compute mij when I is lower than j, we take advantage of the structure of an optimal solution from step 1. We take advantage of the structure of an optimal solution from step 1. Okay, I do get what they're saying, but what is the basis on which they have divided these two parts then? I guess in this part, they did say what an optimal solution would look like, but they didn't define a function for it. I think that is why they have divided these this thing in two parts, a recursive solution. Uh-huh. What an optimal solution looks like. Okay, I will have to talk to ChatGPT for a while to understand that a bit, why they have divided this into two steps. In the first part, we are defining how an optimal solution would look like, what it would look like. And in the second part, what it is, what it would actually be if we have solution to the subproblems, defining it recursively, like here. And this is this is not text, this is a photo, which is funny. We can define this, and we did that part. MII equals 0. To compute MIJ when I is lower than j, that is a non-trivial instance of the problem, we take advantage of the structure of an optimal solution from step 1. Suppose that an optimal parenthesization splits the product this between AK and AK plus 1, where K is might be equal to I, but definitely less than J. Then MIJ equals the minimum cost from I to K, and for computing the left subproduct, and MK plus 1 till J for computing the right subproduct, plus the cost of multiplying these two matrices together, because each matrix AI is PI minus 1 into PI. Each, yeah, those are the dimensions for the ith matrix, PI minus 1 and PI. Computing the product for this particular thing when we are splitting this at K part would be the cost for multiplying matrices I till K, the cost for multiplying matrices from K plus 1 till J, plus the cost for multiplying the left matrix with the right matrix, which is the number of rows in the first matrix in the left part, which is going to be AI, which is going to be PI minus 1, and the number of columns slash rows, where columns are for the first left matrix and rows are for the right matrix, and they are both equal to PK. And Pj is the number of columns in the right matrix, at the end of the right matrix, which is what we get from the right side. This recursive equation assumes that you know the value of k. Yes, we can iterate through the value of k from I till j minus 1, but you have to try all possible values of k. That is, I guess, a subtle but nice point. They have defined that we split this at some region k, but we don't know what k is, and there is no way of avoiding going through all values of k. Therefore, we have to must go through all values of k. How many are there? There are just j minus I number of k's. Yeah, j minus I number of k's. Yep, j minus I. Since the optimal parenthesization must use one of these values of k, you need only check them all to find the best. Thus, the recursive definition for the minimum cost function is this: find the minimum where j goes from I till k goes from I till j minus 1. Yeah. MIJ values gives the optimal cost of values give the costs of optimal solutions to subproblems, but they don't provide all information you need to construct an optimal solution. If you want to construct an optimal solution, we would need some extra information. We would like to need Sj, something like Sj, to be the value of k at which you split the matrix. Okay. Okay. We need some information about where we are splitting the matrix. Cool. If you want to construct the solution, which we are representing. Shit, I messed up. which you are representing with this cuts. This has the things that we need to find the optimal solution. So that is cool. And LSP info, LSP is off. Yep, LSP is off. The log size is massive. That 77 MBs. Why do I have 77 MBs of log? Anyways, we can go where on to the third step, computing the optimal costs. At this point, you could write a recursive algorithm based on recurrence to compute the minimum cost mi till n for multiplying a1 to an. But as we saw for the rod cutting problem, and as well as we shall see in section 14.3, this recursive algorithm takes exponential time. There is no better than brute force. This is no better than brute force method for checking each way of parenthesizing the product. Fortunately, there aren't all that many distinct subproblems, just one subproblem for each choice of I, J, and K, satisfying this thing, which is more like n square, which is more like n square, and all this. So a recursive algorithm may encounter each subproblem many times. And why have they written this like this? Because for every choice of I, J, we have only one subproblem. That is what they have said. And that also makes sense. That also makes sense. But then why are they adding n? They are adding n because internally we are no 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 no, no. They are adding n just plus n. This in all recursive algorithm may encounter each subproblem many times in different branches of its recursion tree. This property of overlapping subproblems is the second hallmark of when dynamic programming applies. The first hallmark being optimal substructure. Second is overlapping subproblems. That is cool. Optimal substructure means you have the ability to break down a big level problem into optimal subproblems, and overlapping subproblems makes sense. Instead of computing the solution to recurrence 14.7 recursively, let's compute the optimal cost by using a tabular bottom approach. Bottom up approach makes sense. It's like this. They have defined m, where they are going to save the answer, and then they are initializing all the answers to 0, and length should, that is very similar to what I wrote. Length is going up from 2 till n, and I also goes up in that region, which is messed up, which is like actually cool. Can I make some changes here? Is this okay? Then yep, this is like exactly the same code which I have written. Don't use mouse. Which I have written in this part here. Length is going from 2 till the end, and internally I goes from I till I plus 1 minus 1, I plus L minus 1. And I think that is what they have written. Yep, I plus L minus 1. In what order should the algorithm fill in the table entries? To answer this question, let's see what entries on the table needed to be accessed before computing cost Mij. Before computing costs Mij, I need answer to I plus I plus 1, I to I plus 2, till I to I plus, till I to j minus 1, and also for all the subsequent right side matrices which were left in all those operations. Let's us to compute the cost of matrix product Aij first, the costs of products A ik and A k plus 1 need to have been computed for all k equals I to j minus 1. Yep. The chain, this thing left, the whole thing consists of j minus I plus 1 matrices because j and I are inclusive, and the chain I till k, and this chain, which is the chain on the right side, consists of k minus I plus 1 and j minus k matrices. Because yeah, we are adding plus 1 here because k is included on the left side, but k is not included on the right side. It is not inclusive on the right side. Respectively, since k is lower than j, a chain of matrices k minus I plus 1 matrices consists of fewer than the original matrices. So we would like to have the answer for all the smaller, all the matrices all the matrices orders which are smaller in number than what we have here. That is what we would like to have before finding the answer for Aij. Now let's see how the matrix chain order procedure fills in the Mij entries in order to increase the chain length. Let's see how matrix chain order procedure fills in the Mij entries. Yeah, I mean, we don't actually have to go through this matrix chain order, because I wrote the whole thing here, and when I was writing it, I was explaining it. So we don't have to go through this because we already went through it in a way. And constructing an optimal solution, yeah, let's do that. That is not very long, and to be clear, I'm not skipping over things because I wrote the whole thing before here. So this is not cheating in some sense. And now constructing an optimal solution. Although matrix chain order determines the optimal number of scalar multiplications needed to okay, we can look at the code. If I equals j, print I. Cool. I. If not, then left parentheses, print the optimal answer to this one, and then print the Hey, I think in this part, what if we don't use this? If we don't, this is what we get. At least we can add a little bit of space. That actually looks cool. Shit, that is much better. That is much better. A2 into A3 and A1. That is much better. That is much better than this thing, uh, this thing, which was before. This looks much better. And the like improvement is only in the aesthetics part, thanks to this thing. And now let's do a bunch, like 6 exercises to see what we have learned. It would be nice. Uh, yep, let's go through the exercises. Find an optimal parenthesization of a matrix chain product whose sequence dimensions is this. Touch. We can solve this. Okay, actually, instead of instead of saying like brute forcing this solution here, let's say int n, c in n, and yeah, c in n and size n for int reference x in v capital, c in x. That is like actually pretty nice. Run it, and in this we have 1, 2, 3, 4, 5, 6, 7 things here. Can we put them side by side? 7 things, and the first one is the things are 5, 10, 3, 12, 5, 56. 5, 10, 3, 12, 5, 50, and 6. Is that correct? 5, 10, 3, 12, 5, 50, and 6. 5, 10, 3, 12, 5, 50, and 6. Yes. And the optimal answer seems to be 2. Wait, is that a reference to something else? I don't know. Now, give a recursive algorithm matrix chain multiplication, and yeah, also this is the answer. This is how we multiply them. Give a recursive algorithm matrix chain multiplication ASIJ that actually performs the optimal matrix chain multiplication given the sequence of matrices this. The S table computed by matrix chain order. Okay, S table is how we compute them, and the initial calls is this. Assume that the call rectangular matrix multiply AB returns the product of matrices AB. Let me just go to the washroom and I'll be right back in a minute. Not that I don't know the answer and I'm going to the washroom to see the answer. I'll just be right back. I have to take a leak. And I'm back. Totally back. And yep, so this is the second question that we have to do. In this, we have to write or maybe just define a way in which we actually perform the thing, perform the operation. So when j minus I, we will first of all call this function for yeah, we can just keep calling this function like this, and yeah, exactly like this. And when I equals j, we will return a, and this thing is supposed to return one matrix, and this thing is supposed to return another matrix. And when we get these two, we will call regular multiply AB, and we will return what matrix is returned by this and by this and multiply the two. So that will be it. Use the substitution method to show that solution to the recursion. This is this. Okay. 14.6, and the solution to this is this, and omega is worst case. No, omega is average case. I have to work on big O notation. Recursion at 14.6. which is this one. This recursion. No, no, this one. 14.6. We have to prove that it is similar to 2 power n. Let's attempt that. Yo, how are you? How are the preparations going on? Tomorrow you are going to be on the flight to Japan. That is cool. Nihon. Konnichiwa. 俺はモンキー D. ルフィ海賊王になる男だ。And yeah, this is the recursion. Pn returns 1 when n equals, wait, it returns 0 when n equals 1. Huh? It returns 1 when n equals 1. What the heck even is it? The number of ways to parenthesize matrix. No, I know Japanese just from anime. I packed my bags and a gift. Shit. That is very smart and that is very mature. Give a gift. Yes, of course. Give a gift. Give her a nice gift. That would be nice. And yeah, my Japanese is just comes from anime, watching a bit of anime. Yeah, giving gift. Shit. If I was going to meet someone, I would have forgotten to take a gift. This is very nice. Very nice of you. And P K plus P n minus K, where K ranges, K belongs to 1 till j minus 1. That is j minus 1. I don't know. School I learned Russian. Shit, привет, comrade. Привет. Wait, where did you learn Russian from? Duolingo? Duolingo right now is very bad. Have you tried Duolingo? It is very bad. It has now those battery feature, which is very bad because at max you can only do 2 or 3 lessons at best with that battery feature. And if you want to fill your battery, you are spending more time watching ads than actually learning. So Duolingo is not very good if you do not have the premium subscription, but I think you might have. I had a Russian friend. Had shit. Uh, Vlad, Victor, Ivan, Vladimir, something like that. And how do you win given a recursive function? Let's draw the tree. How many calls is this going to make? This is going to make a bunch of calls. Shit. This is actually going to make a bunch of calls. This whole part is going to repeat for j minus 1 times. And in one time, we are needing 2 calls. 2 into j minus 1, which is initially n minus 1, pn 2 to n minus 1. And those internally will make a bunch of calls. And they will keep making calls. Yeah, Vladimir or Russians are Vladimir. His name is actually Vladimir. That is funny. Vladimir Kozlov was his name. Was he went back to Russia? Was Vladimir? That is funny. And I don't know this. Uh, Given a recursive function, how do you define how many number of ways, how many times it is going to run, right? Yeah. Oh, he went back to Russia. That is cool. Shit, all of your friends are from other country. Shit, I am from another country, and they all went back to their respective countries because of the war. Shit, all of them are going away, and now you're going to meet your friend. That is cool. Maybe you can say hi to him while you are going over Russia. Just wave your hand from the plane. Mm. Yeah. And how could you actually do this? Like this thing? Pn function is like this function itself. Okay, let's actually draw some shit. Shit. Put some shit on this wall when I get back. That is a meme. Pn is going to make in total 2 p 2 into n minus 1 calls. Yes, 2 into n minus 1 calls on this layer. And how many layers are there? Since it is being reduced by 1 every time, we could say that there are n layers, and in each layer we have 2n times. So kind of like 2n minus 1 into n. But that is not even good, because when I make this many calls on the next layer, I am going to make 2n minus 1 into 2n minus 2 calls approximately. And they are, I guess, in that formula they are somehow ignoring this n minus 1 part, and 2 into 2 into 2, and since the size of this thing is n, so 2 power n is what they came up with somehow, I think. Yeah, lol. I'll say, hello comrade, lol. Yeah, he used to play good guitar. Shit, they have nice voice and they have a lot of pain. Have you heard that song? I thought of learning Japanese, but this stuff, yes, she understands and can speak, so I didn't find it necessary. Yep. Yeah, and Japanese is pretty hard. And the guitar song, have you heard that Russian guy singing in a building where war is going on? He goes, "Don't tell my mom that I'm going to Bakhmut." That song is pretty nice. A guy where there are bombs going on all around, and he's sitting at the top, or like in the balcony of a broken building, and he's singing a song. Don't tell my mom that I went to Bakhmut, because there is war going on in Bakhmut. Yeah, Russian guys are emotional, not emotional, but they have a lot of emotions. Yeah. Lex Friedman, Eric Weinstein, and yeah, I guess we can consider this one done in a way. I will have to read about induction, not induction specifically, but recursion. That would be helpful. And how's your lead code things going on? And I heard Russian drink vodka and pet beers. Russians are very strong. They are very strong. They are very strong. They drink a lot. Yeah. I think, but in drinking, Irish people can defeat Russian people in drinking specifically. But yeah, Russian have a culture of drinking. Dostoevsky is Russian. He's very strong emotional wise. Yeah, they have seen a lot. Russian people have seen a lot. They have seen a lot. Tsar, serfs, they have seen a lot. Describe the subproblem graph or matrix chain multiplication with an input chain of length n. Subproblem graph. Okay. How many vertices does it have? And how many edges does it have? And which edges are they? That would be a good question. Let's say we have three matrices, A1, A2, A3. A2 and A3. And the subproblems that we are solving, let's define this ij as in our solution response as what would be the best cost for multiplying matrices starting from I ending at j. I and j are inclusive, so we would the answer that we need to our big level answer is 1 comma 3. That depends on 1 comma 1, on 1 comma 2, on 1 comma 3. No, shit, it does not depend on itself. There are no cycles here. And yeah, yep. I hate drinking and smoking. I do not hate and drink and smoke. That is bad. Like Trump. Trump doesn't drink. What is left when you start solving problems? What is left when you start solving? I tried once red wine, and that is was my chief told me to try in an occasion, but it sucks. Congratulations for you. Thank you. Thank you for that. And what do you mean by what is left when you start solving problems? I do not get the question, I'm afraid. And thank you for 1K subs. You are one of the subscribers, so thank you. Uh, yeah, I mean, even occasionally you did 250 plus. That is pretty nice. That is pretty nice. 250 plus. And I suppose you are also reading things while you are solving questions and getting much, much better than you were a few months ago. Bro, that is that is necessary. That is necessary. Reading, studying is necessary because from now on, problems are not going to be easy. From now on, we are at 1500 level in the sheet, and these are hard problems. I need to study, and I'm reading this thing on the stream and off the stream. Today, I have to start reading uh, about range queries from Competitive Programmer's Handbook. Range queries, this part, because I suck at range queries. This might seem boring, but it is important. Started gaming as well. Shit, that is cool. I guess one day I will make a game and you can play that game. And hello again, Eric. Uh, yep. So right now I am doing this question for the matrix chain multiplication. I have to draw the sub problem graph, and here is my bloody attempt. This thing node ij represents what is the minimum number of scalar multiplications required for a matrix chain beginning at index 1 and 3, and I and j are inclusive. It depends on these things. Okay, let me make a beautiful one. Let me make a beautiful graph. Okay, it will be very beautiful. People will be jealous. 1 comma 3. Look at this. This is very beautiful. 2, 3, 4, 5. I don't know. See how many do I need? 1, 3. This depends on 1, 1, on 1, 2, or not on 1, 3, not a cyclic dependence, and 2, 2, and then 2, 3. Okay, that was perfect amount, and 3, 3. Those are the things that this one depends on. Yep, and one line here. Cool. And what do these depend? This is a base case. This doesn't depend on anything. This is not a base case. This does depend on one thing. This would depend. on 1 1 actually, and on 2 2. And then this thing is also not a base case. This would depend on 2 2 and 3 3. And yeah, that is cool. That is cool. So here we have 1, 2, 5 plus 1, 6 vertices, and 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. That is the answer. Here you go. But we made it for one specific case when n equals 3. They are asking for n general case. This is good enough. This is good enough. I guess a better representation would be if I move these things below, let's say somewhat like this, and this thing can also go down because that is a base case. This thing can also go down. Should go down in history. That is good. And this, yeah, that looks cool. 1, 2, 2, 3. Yeah, that is good. That is good. I used to play Delta Force and stopped playing, but I started again. I'm thinking about buying a teddy in Japan to big teddy. Okay, because as far as I've heard, Japanese find these okay as a gift. That would be nice. That would be nice. You should buy one iPad. It makes note taking easier and you can make notes more precise and good. Okay, looks like B2 Bomber note. That does look like a B2 Bomber Spirit. Shit, not Spirit. It's a Spirit, B2 Spirit. Yeah, it's B2 Spirit. I like actually I do not have enough money for it right now, but when my YouTube channel grows, I will earn money and I will get a job and I will buy a new iPad. That would be cool. In a while, right now I have to read these things. Dynamic programming. First, I will complete all of this chapter, this whole chapter, and then I will get to the thing. And tomorrow we will read elements of dynamic programming. That is cool. It is going to be cool. Elements of dynamic programming. Because I have not read this part, not even once. So it will be cool. Subtleties, right? We will read about subtleties. Dependence. This is circular dependence. That is bad. And that is just text. Just text. Okay, we also have some graphs. We also have some formulas, some code. Memoization. This is going to be very fun because this will make me very, very strong. Very strong. And then we will solve this question. Longest common subsequence. And if you go to CACS website, which is right here, which is like right here. There is in dynamic programming longest common subsequence. Only 5,000 people have been able to solve it. So that is a hard question. Any company would be nice. Yeah, any company would be nice. Like first of all, I have to like become good enough, and I guess wherever I find a nice opportunity, it would be nice. I don't have a dream company or something like that, but any company would be nice where I see that I am getting challenged. My dream is NVIDIA. Yes, I guess you talked, not you specifically, but the person who won the hackathon got to talk to NVIDIA person, NVIDIA employee, and you went to a hackathon. That was nice. And getting back to the questions, we did this one, now this one. Okay, there is a hint. Let Rij be the number of times that table entry Mij is referenced. Okay. While computing other table entries in a call of matrix chain order, show that the total number of references for the entire table is n cube minus n by 3? That is a good question actually. Better than drawing a B2 spirit. That is actually nice. Cross stream mirror of last year ICPC prelims later today. So that is nice. You is it a thing that you only solve ICPC questions? Because I think you only solve ICPC questions, and if you do solve other questions, you do not talk about them. And how is it that you remember every ICPC question? You seem to remember every ICPC question. You just said earlier today that there is this question in ICPC 2023 where we have a nice DP problem of this sort. How do you remember these questions like by year and by name? Lead code 1143, longest common subsequence. Yes, it is a hard question. No, I do other things also. And this is the third time that you have asked this question. You commented this on one of the videos and you asked this yesterday, but yeah, I do other things also. Like I like to read books, novels, and I don't go to gym. Yeah, gym is bad. I don't go to gym. I exercise at home because the competition is in 2 days. So I have been grinding a lot of ICBC. Shit. Yes, competition is in 2 days. South Pacific. All the best. All the best. All the best. I hope you be really good. You perform. You do your best performance ever. The fun problems is very, yeah, that is nice. And I hope that you give your best performance ever in that, in the contest. I do waste time, like I I do waste a lot of time. All the best, Eric. Rock says all the best. Shit. There are 3 people right now, which I can confirm are watching, and here it says 1. Now it is 2. All the best for your thing, and yeah, all the best. And this is a nice question. How many times are we referencing that subproblem? Wouldn't hmm, we are referencing it from I k. Let's say we are referencing I k, and here instead of making k the iterable, let's say I is the iterable and k is fixed. For k, let's say we have n things, let's say k is at 2. When k is at 2, so let's say I was initially 1, I was 1, and not even that, shit, since we also have j on the other side, which is also changing, and for I equals to 1, j could range from 2 to 3 to 4 to 5 till n, and at every point we will be trying to find answer for I1 2. Yes, shit. In this part, j is the thing that is changing, right? J goes from k plus 1 till n. So for every pair like this, for every shit, okay. For every pair I and k, let's say, we are referencing it in total n minus j goes k from k plus 1 till n. K plus 1, this plus 1, yeah, plus 1, k plus 1 till n. So we are referencing this n minus k plus 1, which is k plus 1, and plus 1 because k plus 1 is inclusive and n is also inclusive. G will be equal to n at the end, and at the start it is equal to k plus 1. So if we solve this we get n minus k times this. So two things are changing. I goes from 1 till n. K, not this, that bad. Shit, eraser. K goes from I till n, and individually, in each case, we are doing n minus k. You have to add that. So what would be the solution to this thing? We can just take n common outside. Uh-huh. Yep. Yes. We can take n out of this summation, and we would have something like ni equals 1 till n outside I times n into I summation k equals I till n, not I, n minus k. If I have n minus k plus n minus k plus 1, n minus k minus 1, because k is increasing and k is negative. So at the end, this will become plus 2 plus 1, and we start with n minus k. We start with n minus I. In this case, k starts at I. So summation till n minus I, which is n minus I into n minus I plus 1 by 2. So we can write this as summation till n I equals 1 into n minus I into n minus I plus 1 1 by 2, 1 by 2 outside. And I wouldn't know how to solve this summation. Surely this would end in something like this: n cube minus n. I'll be in competition someday too. Yep, cool. I gotta leave. Got some SQL knowledge here. Okay, all the best. Bye. And now we have to solve this thing. I is ranging from 1 till n, and for each I individually we are doing this. What if we open this? Yes, of course, that is what a mathematician does. And we open things. Open this, and internally we will, that is like too big. Okay, yes. Internally we will have I equals 1 till n, and on the right we, let me just rewrite. No, I won't. Yeah, let me just rewrite it. From n minus 1, n minus I till n, and that is just beautiful handwriting, equals 1 by 2, not handwriting, mouse writing, and as I from 1 till n, and n square minus n I plus n minus I, n plus I square. And I'm getting triggered because of this I. It feels like in a question I means under root minus 1. That is what I means in a question, but it is not that in this case. This is what we want. I square. What is the summation of this thing? N square. It is, wait, this is constant. This is constant. This is constant. So n cube. I am very stupid. No, this is going to be n square, and I messed up when I brought one term out of that inner summation. I messed up there. No, that was fine. And this is also fine. This is also fine. We are adding stuff. Yes, this is also fine. This is also fine. So this is going to be n cube when I take this out, minus n into summation of I from 1 to n is n into n plus 1 by 2, the whole thing. And this, so I can remove this 2 because half plus half plus n square plus, now is the thing, all right? Now this should be n into n plus 1 into 2n plus 3 divided by 6 and minus n into n plus 1 by 2, n into n plus 1 by 2, and whole thing is half. That might be correct. I don't know. Let's see. How do we do this? Okay, n cube from here, and from here also n cube minus n square plus n square plus, yes, let's just open everything, or not yet. Yeah, let's open it up. N into n plus 1 divided by 2, and on this side 2n plus 3 by 3 minus 1 1 by 2. Okay. uh, uh Wait, did I mess up? Everything is 0 now except these two terms. N square plus n whole thing by 2 into 2n plus 3 minus 3 by 3. Think I messed up at some point, but the order is n cube, so that is a good sign. 6, 3 would be 0 into 2n, so this would be 2n cube plus 2n square, and I can cut off that 2. So n cube plus n square by 6. Don't tell me that is the actual thing. Okay, oh, shit. Okay, it is off by a little bit. The actual answer is n cube minus n square by 3. At some point, I did mess up. That is pretty close to the actual answer. Anyways, okay, I can look at it later. Let me find equation A.4 on page 1141. Why does it like 3.14 value of pi? Okay, 0.26. That is what we do now. So that this was pretty close, very close. And how did we get to this point? We had two summations and we opened them up and we used logic to open them up at every single step. Then we got this, we multiplied the inner things, and we wrote the formula for summation for those inner things. And that worked out automatically. Show that a full parenthesization of an n element expression has exactly n minus 1 pairs of parentheses. Let's begin the Donald Knuth way. When n equals 1, we have no parentheses. When n, this is not n. When n equals 2, we have 1 parentheses. This one. And when n equals 3, we have 3 parentheses, 2 parentheses. A3. So we can, okay, this is our base case. Let's define a recursive function. We have seen a pattern. So we are saying that when n equals 1, light is tripping off, like Tame Impala song. So we have n equals 1, answer is 0. And we are saying that we know, let's say Pn gives us the answer for n parentheses, and we are saying that Pn plus 1 will be equal to Pn plus 1, because whatever the answer for Pn is, it would have something like some form like this, and this thing would have n, this thing would have n, I mean n matrices in total, n pairs, n matrices in total, and when it has n matrices in total, it will have n minus 1 pairs of matrices. And when we add our new matrix, we can say that we add it on to this side or any side. Let's say call it an plus 1, and then we add another pair of parentheses. So for Pn plus 1, the answer is the number of original pairs we had in when we had n matrices, and plus 1 this extra pair. That is the recursive hypothesis, and I guess that is correct. And for this recursive function, I also have a closed form function that I want to say is correct, which is Pn equals n minus 1. So if we plug in this closed form function into this problem, Pn plus 1, for Pn we have n minus 1 and plus 1. So Pn plus 1 equals n, which if we state in this form, we will have Pn plus 1 equals n plus 1, the number of parentheses, the number of matrices minus 1, which is equal to P, which is equal to n. Therefore, by that is too small. By induction, read by induction, this thing is proven that this formula is correct. This formula is correct, and therefore this question can be considered done. And therefore, and yep, that would be for today the end of the stream. And thank you for being here. Bye.